Okay, thanks very much. You can hear this okay? Sorry. So I'd like to thank, excuse me, thank the organizers for the invitation. It's really a great pleasure to be here, and for the hospitality last night. And I'd like to thank you for turning out the morning after the hospitality last night. It's always usually a little hard. Okay, I'll begin by apologizing that this talk really isn't about groups, okay? There's growth and there's symbolic dynamics. There's lots of symbolic dynamics. But I'm afraid I think all my groups are abelian, and worse than that, they're not, most of them aren't even finitely generated, so kind of disaster. Okay, wait, that's too far. Now I'm really confused. Let's go back. Can we go back to the start? No, wrong button. Hang on. Okay. So the talk begins with the work of Smale in the 60s on smooth dynamical systems. So diffeomorphisms of compact manifolds. And the key, he introduced Axiom A, which I won't give the definition, but the key idea is you look at the non-wandering points. Now, it doesn't matter what that means. It's a kind of a recurrence condition, okay? It's closed and invariant. And he said the idea was on the non-wandering set, you should see hyperbolicity. And hyperbolicity, roughly, is you have complementary coordinates of contracting and expanding directions, okay? Now, if you want to see contracting and expanding and you have a smooth map, you use the derivative, okay? So the idea is you should take the tangent space, but only look at it on the non-wandering set, and it should decompose into a stable part and an unstable part, so that just means contracting and expanding. And you see that the derivative on the stable part, the derivative contracts vectors at this geometric rate. Okay, this lambda is between 0 and 1. Expanding, for technical reasons, it's better to say the inverse contracts, okay? So the inverse map on the other complementary space contracts in a similar sort of way. Now, this involves, obviously, a choice of Riemannian metric, but it's independent of the choice, okay? So that doesn't matter.
Can you remind what is the non-wandering point?
Yeah, if you take any neighborhood of the point, no matter how big, there's some point in there that maybe not your point, but some other point that will return in a finite number of iterates. Okay. So the complement, the wandering points, is if you find a neighborhood which never returns, and then it's obviously open because every point does that. Okay. Okay, now his other great observation, or one of the many, was that this non-wandering set is usually not a submanifold. It's typically some sort of fractal, Cantor set, gasket, something like that. So this prompted David Ruelle to say, well, what would be the dynamics if we just looked at the non-wandering set? Okay, just see what the dynamics looks like there. Now the catch with that, of course, is you've immediately lost the tangent space because it's not a manifold. So Ruelle said, okay, we should have a compact metric space and a homeomorphism. And oh, okay, so this is not the precise definition, and the only thing I can tell you is you don't want to see the precise definition. If you're not familiar with these things, it's very opaque. But the heuristic, I'm hoping this will be good enough heuristically. So for a point, you have two sets containing X called the local stable set and the local unstable set. They also have a parameter epsilon, and it's like an epsilon ball. It's just designed to control the size. The Cartesian product is homeomorphic to a neighborhood. And if I was giving a precise definition, I would say what that homeomorphism is, and it would have some properties, but let's not worry. Okay, if you do this at X, and you do it at phi X, you have two product structures, and somehow the map should kind of respect those product structures. Okay, again, that's vague. Now, the third condition is the important one, and it's not vague, okay? If you take two things in this local stable set, you apply the map, the distance is contracted. And in the unstable set, the inverse does the same thing. Okay, now I don't want you to feel like you've been cheated out of a definition. So are there any questions?
Do you want expansivity?
It follows. Okay, yeah, well, from the precise definition, yeah, expansive.
So you want all the points to be non-wandering?
No, that's curious. I thought for years you did, but it turns out that you don't. Yeah, and that's a little weird, but it's better to allow they don't. Okay. Okay, maybe I can even say why if I remember in a minute or two. Anything else? Okay. Now, I'm going to give you some examples in a minute. The only thing I'd want to say about the examples now is when you see them, you're not going to see them sitting inside manifolds. And that's why I like this definition of Ruelle better than the Axiom A. Okay, so if you like pictures better than the words, there's the definition. Okay, that's it. I mean, if you remember one thing of the talk, that's it. Okay. Now, in a Smale space, there's lots and lots of periodic points. So if every point is non-wandering, the periodic points are dense. In general, they're dense in the non-wandering set. On the other hand, for every finite period, there's only a finite number of them. So it becomes an interesting issue to count them. So the number of points of period n is called per n x phi. And okay, so here's the growth, okay, right? So how do they grow? Well, this isn't too terribly hard, at least for mixing systems. They grow exponentially, and the base is the entropy of the transformation. Okay. Now, on the other hand, much more subtly, Anthony Manning proved the following. If you take those numbers, divide by n, and make a formal power series, and exponentiate e to the 2 pi I times that, this is the Artin-Mazur zeta function, and Manning proved that this is a rational function. Okay. Now, that prompted Bowen, and it's a natural sort of question, but asked, is there a homological interpretation of this? Okay. And by that, what you want is there some sort of homology theory which provides a Lefschetz formula? Now, if you don't know the Lefschetz, you'll see the Lefschetz formula eventually. Okay. Basically, what this is meaning is that this number, you have a finite dimensional vector space and a linear transformation, and this number is simply the traces of the powers of that. And if you have that, then this sort of theorem follows kind of easily. Okay. So that's the motivation. Okay, so this is the question. There's the answer. I could sort of stop now, but I think I'd like to say more about it. So I hope if you don't mind. Okay, so right. Let's go on and give some examples. So the simplest example possible is just take. This is the most famous matrix in dynamical systems, 1, 1, 1, 0. And you just look at it as a linear map on R2. And OK, it has an eigenvalue bigger than 1. That eigenvector is expanding. It has an eigenvalue. The other one's between minus 1 and 0. So that's contracting, OK? And that's hyperbolicity. Now, of course, this isn't compact, all right? It's also not an interesting dynamical. Linear maps aren't interesting dynamical systems. But the matrix has determinant 1, or minus 1 rather. And so it preserves the integer lattice. And if you pass to the torus, the quotient, I mean, the local structure of the map doesn't change at all, right? I mean, and everything is in terms of local structure. So this is an example of a Smale space. Notice the stable set and unstable sets both look like the eigenspaces, and those are just reals, okay? Oops, I'm going to eventually get used to these buttons. Okay. And oh, I'm pointing at the wrong thing, too. Okay, shifts of finite type. So here's the symbolic dynamics. And probably, well, we've seen these before, and probably everybody knows. You take a finite directed graph, and you look at infinite sequences. I'm using superscripts for some reason. Okay, so you look at infinite sequences in the edges which form a path. So you're just looking at infinite paths through the graph. And the map is the left shift map. So you just shift the sequences over. I've even given you a definition of the metric. If you have to use the right metric to do this. Now, probably lots of people are familiar with that, and you know, this may not be new. Why is this? You may not be familiar with the fact. Why is this hyperbolic? Okay, so let me show you why it's hyperbolic, and I'll do it only for a graph that has 2 vertices. So the vertices are v and w. Okay. Now, any doubly infinite sequence has a central vertex, where edge E0 ends and edge E1 begins. There's a vertex there. So let's call that the central vertex. It's either V or it's W. So that divides the space into 2 pieces. Okay? They're both clopin. On the other hand, you'll notice that the pieces are not just blobs, they're rectangles. Why are they rectangles? Well, any sequence in here has a forward coordinate and it has a backward coordinate. Okay, it's a product space. Okay, and I'll let you think about if suppose 2 sequences had the same forward coordinate. So suppose you had 2 sequences that look the same. Now shift them over, what happens to the distance? Well, it gets smaller because where they're differing is being moved away. Okay, okay. So there's shifts of finite type. Of course, these are totally disconnected examples, and both contracting and expanding directions here are Cantor. Okay. In fact, every totally disconnected Smale space appears through this construction. Okay. 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 So the next example, you take the solid disk.
What was the graph for previous example?
What was the
Graph.
any graph?
Previous example.
Any graph. Well, okay, if it has no cycles, then it's the empty set. But I mean, any graph. Oh, and so in answer to your question, if you took a graph with 2 loops and 1 edge, then the points aren't non-wandering, but it's still okay. It's still a Smale space. So no, sorry, but did I answer? Any graph at all.
And your lambda was 1/2 in that case?
Yeah, lambda was a half. Well, the metric I gave you. Yes, very good. Anything? Okay. Okay, the next one, yeah, solid disk cross a circle, which is what you see here in the pale green, okay? In Canada, if you show this picture, people start thinking about the coffee break, but I don't think you have these in France, right? So, okay, so, and you define a map of that into itself, and the dark green is the image, okay? So you can see what's happening. You're just taking the tube and you're wrapping it twice around itself. And let me just say what's completely obvious from the picture is that the disk is getting contracted and the circle is getting stretched. So that's hyperbolicity, right? Now, it's of course not a homeomorphism. So what you have to do is here, keep applying the map and the images get smaller and smaller and smaller. You intersect them all, and on the limit, you get a homeomorphism. Now that turns the disk into a Cantor set, okay? When you do that process, and the other direction looks like a circle or a real line, at least locally. Okay, this is an example that I kind of have gotten to love over the last couple of years. So we're going to take 2 prime numbers, p and q. Let's say p is the bigger one, and I'm going to look at the p-adic numbers cross the real numbers cross the q-adic numbers, and my map is simply going to multiply by p over q in every coordinate. Okay. Now, the cute thing about that is on the p-adics, q is an isometry, while the p inverse expands. On the reals, well, q over p expands just because I said q is bigger. On the q-adics, p is an isometry and q contracts, okay? So you get expanding, expanding, and contracting. Again, this is not, space, of course, isn't compact, but there's an invariant lattice, which is the subgroup of the rationals generated by the 1 over powers of p and q. And on this quotient, well, you still have the same local structure, and it's now compact. Okay? So here we have Cantor and Cantor cross R as the 2 coordinates. Okay. Okay, now here's an example you'll like better. This is my one non-abelian group, but it's not mine, it's Volodya's. Okay. So let's take a self-similar action, which we've seen, which is self-replicating. I won't give the definition because I don't remember what it is. It's contracting, which fortunately Laurent defined yesterday. Now regular. Now this is a little subtle. It's at sorry. What is this? Of course, this group is acting on a tree. I want to look at the boundary of the tree, which I think of just infinite sequences in this finite alphabet. Okay. So the group is acting on the boundary of the tree, and you want the fixed point sets to be open as well as closed. Okay, and that's sort of subtle. The Grigorchik group does not do that, but the Basilica group does. So there's some examples. And so how are we going to make a Smale space? Well, instead of looking at the one-sided sequences, let's look at the two-sided sequences. Okay, and we put an equivalence relation. The 2 sequences are equivalent if you can find a sequence of elements in the nucleus. This is as Laurent defined. Actually, I think they could more or less be in the group, but let's just say they're in the nucleus for technical reasons. So that when you act 1 on Gn, it converts it to Gn plus 1, and the next group element is the next element in your sequence. So let me just say what this little equation is in terms of how Laurent said this. So Gn gives you a permutation of the set A. So it should take xn to yn, first of all, and then the label that gets, the next group element that you put on that label is Gn plus 1. Okay, so that's the equation. So you take the quotient. Now, this is all shift invariant, so the shift map descends to the quotient. You get a Smale space. And if you, for instance, used for your group the iterated monodromy group of some rational function with some hypotheses, what this looks like, the contracting direction is Cantor, and the expanding direction looks like the Julia set for the map. Okay, is that all? Okay. Now.
Did you say what is n-tech?
Which is?
N-tech previously.
Sorry? No, wait. Finite hyperbolic?
N-tech.
The nucleus.
No, N is the nucleus, yes. Yes, yeah, okay. His definition's a little different, but this is a theorem that's equivalent. It's, okay, yeah, okay. Okay, so I'll remind you the aim of the talk is we want to take all these Smale spaces and define a homology theory for them. And it's 2 steps. So the first part is an invariant that was introduced by Wolfgang Krieger back in the 1980s, and it's just for shifts of finite type. So somehow we just attack shifts of finite type first, and after go to the general case, okay? So that's the second step. Now, so I want to describe what Krieger did, and to motivate it, I'm just going to talk about how do you compute the cohomology of a compact space, okay? Well, you take an open cover, right? Take a finite open cover, and you look at where the different sets overlap. So you look at pairwise intersections, three-way intersections, and so on, and keep track of all that data. It's called the nerve of the cover. It's a simplicial complex, okay? So, and once you have that combinatorial data, you do some computations, compute the homology of the complex, and then at the end you refine your open covers and get an inductive system. Now, if your space is totally disconnected, and remember shifts of finite type, the spaces are totally disconnected, there's particularly nice open covers. You just partition into Clopin sets, right? So you just partition the thing into a finite number of Clopin sets. Now, if you do that, all the intersections become trivial. So your entire nerve is living in dimension 0. And basically, when you do this computation, you just get a copy of Z for each of the Clopin sets, okay? Okay, now what do you do? Well, you have to refine these things. And when you refine them in the limit, the cohomology is, it's the abelian group generated by the Clopin sets with this relation that adding 2 of your Clopin sets in the group is the same as taking the union, provided they're disjoint. Okay? So this relation comes when you refine, right? Okay. So Krieger said, let's do exactly the same thing for our shift of finite type with one little, whoops, let's go back. Oh, so what happened to the next slide? There it is, okay. Do exactly the same thing and look at Clopin sets, but don't look at Clopin sets in the space. Look at Clopin sets that just are Clopin in the relative topology in one of the contracting sets. Of course, there's another version where you do the expanding. So here's my rectangle. This horizontal line is the horizontal line here is the contracting set, and you see that I found a Clopin set. Obviously, there are too many of these, right? Because every horizontal line, they're all homeomorphic to each other, right? It's a product space after all. So if you have a U here, it's got a doppelganger V in any other level. And Krieger said, okay, let's just declare those are equivalent, okay? In addition, so we're introducing an equivalence relation. Let's also say that U and V are equivalent if and only if sigma U and sigma V are equivalent. Now, what's happening here? Well, of course, sigma will make U and V smaller, right? But it will also push them apart. And so the sigma U and sigma V may not lie in a rectangle like this, okay? So this is an extra condition. So you, okay, generate an equivalence relation, smallest equivalence relation with all of this. And again, you mod out by this relation that the class of U union V should be the sum of the classes, and you get an abelian group, okay? Okay, so now the first questions I would ask about this is, well, I mean, first of all, is there any hope you would ever compute it, right? And the second question is, how in the world did he ever think about this? So let's answer those two. So can it be computed? How did he think of it? The answer is beautiful and simple. You take the number of, so it's given by, your shift is given by some finite directed graph. You take Z to the n, n's the number of vertices. And the number of vertices, well, there's an n by n matrix, the adjacency matrix, that tells you how many edges there are between different vertices. You just multiply by that adjacency matrix, and then you take the inductive limit of that system. So you compute it easily, okay. Do I have... Okay, let me see. I can actually give you a proof. I can almost give you a proof of this, okay? So let's go back. Oh, and I'm going, okay. You know, eventually I promise I'll get this. So here's our shift of finite type. Okay, so can you see in this picture, this is two vertices, can you see in the horizontal lines two Clopin sets? Yeah, obviously, you take the whole Clopin set across this one, you take the whole Clopin set across this one, that's your first copy of Z2. Okay, what's the next copy of Z2 in that inductive system? You just apply sigma, okay, and contract them. So it's, I mean, if I say that, you can easily construct the whole thing. Okay. Now, okay, so we saw that. Now, how did he think of it? So this is a kind of a word, I mean, I'm an operator algebraist, so this is a word from our sponsors of the operator algebra community. If you go back and, okay, so what did I do? I looked at Clopin sets and took an equivalence relation. What if you do it the other way? Okay, so first take an equivalence relation just on the points of the space. Okay, make the quotient space by this equivalence relation. It's the same thing, just replace u's with points, right? So take, oops. Okay, so take the quotient space by this equivalence relation and look for Clopin sets, which is the Czech cohomology. Now, unfortunately, this is a terrible idea, and this is not what's happening, and it's a good thing it's not what's happening, because if you do this, basically you're getting an uncountable space with the indiscrete topology, and lots of interesting examples. The finite part's just a single point. So this is a totally useless space, okay? On the other hand, when you meet a totally useless space like this as a quotient space, you know what you should have done instead, particularly in Paris, you know what you should have done instead, because Alain Kahn tells you you should have built a C-star algebra instead. And this is actually what Krieger, I mean, Krieger could see the C-star algebra. He knew how to construct it. And this group he got, it's a nice class of C-star algebra, and the group he got is just the K-theory group of that C-star algebra, okay? Now, the impressive part is that Krieger did all this before Kahn was saying this, okay? So it's a nice example. Okay, we're trying to find a homology theory. We've done the first step and found Krieger's invariant, and we're now going to try to extend it to Smale spaces, okay? And to do this, we'll look at a little bit at the proof of Manning's theorem, which contains a couple of important ingredients, okay? So, okay. The first crucial ingredient is Bowen's theorem, which tells you that if you take a Smale space with every point non-wandering, then you can find a shift of finite type that maps onto it. This map is, of course, equivariant, continuous, surjective, and finite to 1. So the shifts of finite type map onto everything. Okay, so you find one of these. Of course, it's not unique. I mean, there's lots of choices. Now, Manning sort of said, well, let's see what happens to the periodic points, and he worked it out. And this is how he proved the rationality. But let me show you one of the ingredients in what he did. So he said, look, I mean, of course, this is mapping onto, but let's just keep track of when is it 1-to-1, when's it 2-to-1, etc. Okay? So he defined these systems, I call them sigma n of pi. Pi is the map. So I want n plus 1 tuples. These are all coming out of the shift space. And okay, so E0 is actually a doubly infinite sequence, and that's why I used superscripts on the sequences. So each of these is in the shift space, but they all have the same image under pi. Now, it turns out all of these things are shifts of finite type. They all obviously carry an action of the permutation group, okay, on this space. And okay, so Manning looked at the periodic point data in all of these systems together with the action of the permutation group and managed to compute periodic points. Okay, but what's interesting here is this is very reminiscent of something we did earlier in the talk, which was to compute Czech cohomology. Czech cohomology, you start with an open cover and then start keeping track of when are these sets intersecting, okay? So let me draw a parallel. So this is between Czech cohomology of a compact manifold versus what we're going to try to do. Okay, so in check cohomology of manifold, you take a good open cover. So good means every set looks like a Euclidean ball. And if you intersect a finite number of them, the intersection still looks like a Euclidean ball. So if you're doing the circle, you don't want to do two halves of two open intervals that overlap like at the top and bottom, because then it's not a ball when you intersect. But okay, so you make a good open cover. Our replacement for that is Bowen's theorem. So the shift to finite type is mapping on, that's our open cover, okay? In check cohomology, you look at these non-trivial intersections or multiplicities or nerve of the cover. These are these systems of Manning that just you're keeping track of when is it 1 to 1, 2 to 1, and so on, okay? In check cohomology, you basically get a group, okay, generated by the non-trivial intersections. But the reason you're doing that is because the non-trivial intersections, each one looks like a Euclidean ball. And the check cohomology of a ball is the integers, okay? So this is really taking check cohomology of these elements here. So on our side, what we're going to do is we're going to take Krieger's invariant for each one of these shifts of finite type, okay? Now, okay, so now you'll notice there's a little on this group, there's an alt, okay? And let me just say this very quickly. I don't want to go into many details. If you look at what's happening with the multiplicities, on the left in check cohomology, these integers here, this isn't a tuple, right? It's a simplex. So you don't care about the order except up to sign of the permutation, okay? Where on the right, oh, gee, that was a disaster. Okay, let's go back. Okay, on the right, these Manning systems, these are tuples, okay? So after you take this group, then you bring in the permutation group acting and take a quotient or a subgroup or something. So this alt is where the permutation group comes into the picture on the left. It came in on the right, upper, a little bit above. Now on the left, okay, you have boundary maps. I've written one of them, but you know how to write the rest of them. And the question is, well, how do you do that here? And the answer is you can't. This is a beautiful idea that falls apart right at this stage, okay? But it's not so terrible that it's not worth telling you. So what's the problem? Well, so this is n plus 1 tuples with the same image. And here are n tuples with the same image. These are shifts of finite type. And you can certainly simply remove one of the entries. You get a nice map between two shift spaces. And oh, by the way, in terms of your question, these ones are almost never non-wandering. I mean, these usually have lots of wandering points. Okay, so this is a nice map between the dynamical systems. The problem is, does it give you a map between Krieger's invariants? And unfortunately, Krieger's invariant is sufficiently complicated, the answer is no in general. But, but this has been worked out by the people in symbolic dynamics. So let me just tell you what they did, okay? Okay. Now, suppose you had two Smale spaces. Suppose you had a map between them, and I'm going to call it S bijective if on the local stable sets, it maps them homeomorphically down. Now, first of all, it's trivial that it's going to map local stable sets to local stable sets. But what I want here is, let's say precisely, if I give you a y and an epsilon prime, you should find an epsilon so that this set, local stable set in the top space, is mapped to an open set here, and it's a homeomorphism to its image. So whatever is happening is not happening in the stable sets. That's just homeomorphism. The unstable sets are where the complicated things are happening. And the relevance is, if you have such a map between two shifts of finite type, if it's S bijective, you do get a map between Krieger's invariants. If it's U bijective, you can guess what the definition of U bijective is. If it's U bijective, you also get a map, but you'll notice it goes the other way. Okay, so it's covariant for one of these kinds of maps, it's contravariant for the other one. Okay, and you know, if you looked at a map, if this was a two torus, okay, this looks like Cantor cross Cantor, and this looks like line cross line. Obviously, the maps are not going to be local homeomorphisms. Okay, okay, so what do? Is we come up with a better version of Bowen's theorem. So what am I going to look for? I'm going to start with my Smale space. I'm not going to cover it with a shift of finite type. I want to cover it now with another Smale space where this map is S bijective. Okay? In other words, the stable sets, the local stable sets between y and x are exactly the same. But the unstable sets disconnect. So instead, where Bowen takes a Smale space and replaces it with a disconnected, totally disconnected space, I want to do that only in one of the two coordinates. And in the other coordinate, I don't want to do anything bad. Okay, so the unstable sets become totally disconnected. The stable sets stay the same. Okay, so it's a one-coordinate version of Bowen's theorem. Okay. Okay, now you can, of course, if you do that, you can do it the other way around and try to disconnect the stable sets instead without disturbing the unstable. And if you do both of those things, we'll call that an SU bijective pair. And the better Bowen's theorem is that these things exist. Okay? So now, let's just go back to Bowen's theorem. If you've got one of these things, you can make this fiber product, or the pullback, okay? That pullback is a shift of finite type. It maps to the y system and then the x system. The first map is U bijective, the second map is S bijective. It also maps through Z by S bijective followed by U bijective, okay? So you're getting a map like Bowen's theorem, but it decomposes in two ways. So that's what's better. Now, this is subtle because if you take one of Bowen's maps, it's not true that any one of them will decompose this way, okay? The theorem is telling you there are some that do, okay? Let me put this in really basic terms. If you go back to the example on the 2 torus, 1, 1, 1, 0, every dynamical systems textbook in the world will show you a Markov partition, and the Markov partition is giving you this Bowen's theorem, okay? Half of the dynamical systems book, the Markov partition will have 2 rectangles, and in the other half of the textbook, it will have 3 rectangles. The 2 rectangle version doesn't do this. The 3 rectangle version does, okay? So it's you know, there's subtle things going on. Okay, now what do we do? Well, now we go back to Manning's idea. Manning was keeping track, when is it 1 to 1, 2 to 1, and so on. Now, unfortunately, we have 2 maps, okay? So, or, you know, there's a map from y and there's a map from z. So we look for L plus 1 tuples from y, M plus 1 tuples from z, all having the same image. So we're just keeping track of when are these 2 maps, 2 to 1, 3 to 1, and so on. Each one of these things is a shift of finite type. And you can now, again, look at the maps which simply erase one of the y's, that goes from L to L minus 1 if you erase a y, or you can erase one of the z's, which goes from M to M minus 1, okay? And the big success now is these first maps are S bijective, and these maps are U bijective. That's what was missing from Manning's idea before, okay? So that's the key point. If we do that, then we can assemble everything together. So we take all of these systems, sigma L, M, for every L and M. We put them into an array. We compute Krieger's invariant on each one of them. We introduce the permutation group, and there's 2 permutation group acting because you can permute the y's and you can permute the z's. So you mod out by or whatever by that, you get this double complex. Now, if you've never seen one of these, it looks rather daunting. Oh, notice the maps. So here, when you erase the y's, you're getting a map horizontally downwards. When you erase the z's, you get a map vertically downwards, but it's contravariant, so that's why the boundary map starts going up. Okay? Now, if you haven't seen one of these things before, what you do is you think of all the groups on a diagonal as one group just by taking direct sums. So that's what's happening here. So you take the groups on a diagonal with direct sums, and then you notice your boundary map is going from one of these groups to the one above it. Okay? So, and this is complex. You take the kernel modulo the image, and you compute some groups. Okay, let's...
Is there some edge on deltas?
With the star? That was my notation. So this, when you erase a y, that's a covariant map. So I put in an S to say what it does on the Krieger invariant. This is this is contravariant. That's why the star is there. So it's going the opposite direction. Yeah. Okay. Okay. Let's just go back a second. Where did we start with? We started here with a Smale space, and we said, okay, there exists this thing that disconnects it. Of course, it's very far from unique. Once you choose that y and the z, then you introduce all these systems. You can introduce their Krieger invariants, you compute all these groups, the maps, you compute the kernel and co-kernel, okay, and you get these answers. The answer you get does not depend on that choice of y and z, okay? It's independent of the choice of y and z. It, of course, depends on x. And so this is the homology theory for the space x, or the Smale space. Okay, it's covariant. Oh, I'm doing great. Okay, it's covariant for S bijective factor maps. It's contravariant for U bijective factor. That's the same as Krieger's invariant was, so this is not such a big surprise. Okay, and all of these groups are finite rank groups, not finitely generated, but they're finite rank. And there's only finite number of non-zero ones, okay? And there's a Lefschetz formula. So if you take the groups, okay, this phi induces an automorphism of these groups. If you turn the groups into vector spaces, they're finite dimensional vector spaces, it's finite rank. You take the pth power of the map and you take its trace, and then you sum with an alternating sign over all the different groups, and of course there's only finitely many non-zero. And if you do that, what you count is the number of periodic points of period p. So this was the goal, was this, this Lefschetz formula. Okay. Let me tell you what happens in the examples. Okay. Suppose you started with a shift of finite type. So what's the first step? Well, you have to disconnect the stable sets and the unstable sets. Fortunately, they're already disconnected, so you don't have to do anything, okay? So you can simply use y and z both sigma. If you do that, that entire double complex I had reduces to one non-zero term which sits in the lower corner of the thing, the lower left corner. All the other groups are zero. And it's Krieger's invariant, and so H0 is Krieger's invariant. All the other groups are zero. If you remember this was this example where I was multiplying by p over q with the q-adic numbers and the p-adic numbers and the reals with our two primes. You get z1 over q in dimension 0, you get z1 over p in dimension 1, and all the other groups are 0. And this is actually, of course, this is not the same as the cohomology of the space, which doesn't, that it's acting on, so that's different. Okay, this was the wrapping the donut around inside itself example, and there's a much more general construction due to Bob Williams of one-dimensional solenoids, and we have worked out with Masoud Amini and Sarah Saidi Golakhandi the answer. So in this example, you get z1 half in dimension 0, and you get z in dimension 1. Okay. Okay. Finally, back to the very first example. So on the 2 torus, okay. So here are the answers. Okay, and you'll notice that it actually coincides with the cohomology of the 2 torus, and there's probably a very good reason for that. There's a dimension shift, though, right? It lives in dimensions -1, 0, and 1. But this is the same as the cohomology of the torus, and this is the same as the action on the cohomology of the torus of this thing. So there's probably some good reason for that, which at this point I'm not aware of. And I still finished a few minutes early, but that's it. Thank you for your attention.
You mentioned the other invariant, the Bowen and Franks groups. Can they be used to get something similar?
Yeah, that's actually a really good question. No, the other invariant is not actually the Bowen and Franks invariant. It's something else that's in that paper that everybody's forgotten about, where they look at transverse invariant measures and show this is a finite dimensional vector space or something like that. Yeah, okay. So the most curious thing about this, if you think of comparing this to cohomology, I'll give you, I think the answer is yes, so let's put it that, but it's not quite the Bowen and Franks, maybe not exactly the Bowen and Franks group that you used this term. Okay, if you compare this with cohomology, the most curious thing about it is, of course, cohomology, I mean, in cohomology you have different forms of it, and of course one of the things you have is check cohomology, you also have de Rham. And okay, de Rham's theorem tells you these are more or less the same thing. Of course, de Rham cohomology, you know, was basically, I mean, it's differential forms and stuff, right? So it predated check cohomology by, I don't know, 100 years or whatever, right? This is Czech, and it seems strange that I don't know what the theorem theory is for these things. So that would be a really, and if you're thinking of the parallels with C-star algebras, it looks like you should use cyclic cohomology on the algebras. Now you have to be very careful of what the algebras are. But the cyclic cohomology looks very much like this Bowen, for the shifts of finite type. Cyclic cohomology looks very much like the other answer, so that's very suggestive of something. I'm not sure what.
Further questions? No? Okay, let's thank Ian again.
Yep.